Okay, folks. Today I'm going to be in my office from 4 to 6 for those of you who either scored less than 1 standard dev below the class mean on this latest midterm, or if for whatever other reason you want to talk to me. Okay? So come over. If you have your exam with you today, please bring it. Or if you have access to it, please bring it so we can have a more meaningful conversation. If you don't, that's okay. We'll still have some chatting to do. If you have a conflict today, you can't make it for some reason because of the short notice, then send me an email with your availability for next week, early next week, Monday or Tuesday. And I'll pick a slot that works for me as well. Mondays are my better days. So again, this is not restricted to those of you who scored less than 1 standard or less than a standard dev below mean. If you're concerned about your grade or your performance in any way, you can feel free to come and talk. But this group must come and talk to me. Because the earlier we intervene, the higher the chances that we can help you out before the end of the semester. If you come to me 2 weeks or a week before the end of the semester, then I can't really help you. All right, let's get back to the discrete Fourier series. We talked last time about expanding x as a linear combination of a bunch of functions or signals, or in vector notation, x being a linear combination. This index is k. X being a linear combination of a bunch of vectors, where x, if you look at a periodic signal, let's say 1, 2, 1, 2, 1, 2, x as a vector is essentially a stacked up version of values within one period. So this is periodic with period. X is periodic with period p equals 2. You pick the values within one period, and you stack them up. So let's say this is 1, this is 2. So you have x0 and x1. And in this particular case, I've drawn lollipops of height 1 and 2. You stack them up as a vector, and you consider some vectors phi k. In this case, how many k's do we need, according to our discussion last time? 2. So we need a phi 0, a phi 0, phi 1 through phi p minus 1. So there are p of these vectors that we need in order to linearly combine and get the vector x. And we looked at 2 of these, 2 types of these. So we had the canonical vectors, where phi 0 was 1, 0, and phi 1 was 0, 1. These would correspond to periodic signals that are impulse trains. So 1, 0 would correspond to 1, 0, 1, 0, 1, 0, and so on. This would be phi 0 of n. Okay? And so in the same way that I picked one period of the signal x and stacked up its values as a vector, I can do the same thing with phi 0. So I pick this one period, and stack up its values and create a vector. And I do the same thing with phi1. So phi1 would be 0, 1, 0, 1, 0, 1. And we gave this whole thing a geometric interpretation in two-dimensional space. So we looked at the two-dimensional space. And we had the first canonical vector, phi0, and we had the second canonical vector, phi1. So this was 1, 0, and this is 0, 1. And we want to, actually, what was the x vector that I used last time? Let's stick with the same one. Was it 2, 3? It was 1, 2? It was 1, 2, okay. So our vector x is this one, which is 1, 2. And our goal is to figure out how much of phi0 and how much of phi1 we need to be able to construct x. How much of this do we need, and how much of this do we need to be able to construct x? So we want to represent x as a linear combination of phi0 and phi1. Now, when the vectors phi0 and phi1 are of the form that I've shown, you can eyeball it. You can immediately tell me what those coefficients are. What are they? How much of phi0 do I need? 1 times phi0. How much of phi1? 2. 2 times phi1. Okay? This is analogous to breaking up the signal x as a linear combination of shifted impulses. This is the unshifted impulse. This is the one-sample shifted impulse, except that I've created a periodic train of them. We've done this several times in the course of the semester. Things changed when we looked at another set of vectors. Instead of phi0, phi1, now look at a different set, of vectors ck, where, for example, in our two-dimensional case, I pick ckn to be e to the I k omega naught n, where omega naught is related to the period. Notice in the previous case, I created an impulse train with the same period as my original signal. This one, the way I've defined it, it automatically has built into it the periodicity. If I change n with n plus p, what do I get? What do I get? Well, we have the first factor, omega naught n. What can you tell me about e to the I k omega naught times p? Why is this equal to 1? Omega naught p is 2 pi. And k is an integer. So this whole thing is 1. So CKs are periodic. In the case where I'm dealing with periodic signals of period 2, I only need 2 of these guys. So if p equals 2, omega naught equals 2 pi over p, which is 2 pi over 2, which is pi. And so my C0 of n is what? When I plug in k equals 0, it's 1, because it's e to the 0. And so when I look at its vector, I get 1, 1. This is C0, 0, and this is C0, 1. The other vector I need is C1. So I plug in k equals 1. I have e to the I times 1. Omega naught is pi times n. And you recognize this as simply minus 1 to the n. So when I look at C1 as a vector, what's the first entry? 1. What's the second entry? Negative 1. So this is C1, 0, and this is C1, 1. So what we want, this is essentially our entry into Fourier series. All we're doing when we're talking about Fourier series expansion is that we're changing the vectors that we used, phi0 and phi1, that we were very comfortable with. We could decompose any signal in terms of a linear combination of impulses. That's that decomposition. All we're doing now is changing those vectors phi0 and phi1 to C0 and C1. So when we look at the picture in the two-dimensional space, we have for C0 the vector 1, 1. This is C0. Okay? Equals 1, 1. And C1 is 1 minus 1. It's this guy. And we're looking at the same vector x, the blue vector up there, which was 1, 2. And we're asking the question, how do you write what are these? How do you write x as a linear combination of these two new vectors? What are these coefficients? That's the whole question with Fourier series. So when I write x as a signal, I'm looking for the combination phi k, xk, phi k n. In other words, I'm looking at the combination xk, e to the I k omega naught n. This is a very powerful decomposition because it tells me I can take any periodic signal and I can write it as a linear combination of these complex exponentials. But they're not just any complex exponentials. And they're not just an arbitrary set. They're a set of complex exponentials whose frequencies are related to each other in a very specific way. So this DFS, the decomposition of a signal x in terms of what is referred to as harmonically related complex exponentials. What do I mean by harmonically related? Can anybody guess? Let me ask you this. Yeah? Well, P is that period. They're all periodic with that period P. But in terms of their frequencies, how are their frequencies related? Multiples of each other. So you have e to the I 0 n, e to the I omega naught n, e to the I 2 omega naught n, and all the way to e to the I, what? P minus 1 omega naught n. In the case of a periodic signal with period 2, you only have two harmonically related frequencies. 0 times omega naught. Omega naught is pi. So if P is equal to 2, then omega naught is 2 pi over 2, which is pi. And all you need is e to the I 0 n and e to the I pi n. This is the simplest case, the case that you can actually draw on the board. And that's why it's nice and we start this way. But the moment you go into P equals 3 and above, you've got omega naught equals 2 pi over 3. So you've got e to the I 0 times that, 0 n, e to the I omega naught n, so it's 2 pi over 3, and e to the I P minus 1, which is 2, twice that frequency, which is 4 pi over 3n. Why do I not care about e to the I 3 omega naught n in that case? Why not 3 omega naught n? It's just the same as this guy. Right? So they cycle. So we only need p of these complex exponentials. Now let's put this in plain English for posterity. If x is periodic, well, scratch that plain English. With period P, the moment you get to speak in symbols, you're beyond plain English. Is periodic with period P, then the only frequencies that can exist in X are 0, omega naught, 2 omega naught, P minus 1 omega naught. There's no other frequency. You can't have a periodic signal with period P and have, for example, omega naught over 2 as one of its frequency components. That's one of the beauties of Fourier series decompositions. So if you have a periodic signal with period P, the only frequency content, when you look at its spectrum and try to figure out what frequencies are present in that signal, those frequencies appear at a discrete set. It's a discrete set of frequencies. Now let's go back to our geometric interpretation. What's common between the C's and the Phi's? They're orthogonal. So when we wrote X as a linear combination of the phi k's, and again as a linear combination, these coefficients will be different from those coefficients because your functions are different. And a linear combination of the ck's, one thing that was common was that different phi k's were perpendicular or orthogonal, and so are the different ck's. And that's a feature that we exploit in finding those coefficients. We exploit this to find the xk's. And that's where we speak about the notion of an inner product, or the dot product. So you look at, let's deal with the ck's. X is, let's write this out. x0, c0 plus x1, c1. Let's stay with the two-dimensional case. I have these two vectors that I'm linearly combining to construct the vector x. How did we find the coefficients? What did we do? Project. And projection is done by what you previously knew as a dot product, and now you currently know as an inner product. So you take, to find x0, project x onto c0. And to find x1, project x onto c1. Projection is done by what you knew as the dot product, but which we now know as an inner product with a slightly more generalized here. I did it the British punctuation and the American punctuation. There you go. Any Brits in the class? No? Well. All right. So let's see what that means. Sorry, I forgot you were all geeks. You're not social science majors. You're not normal people. Whereas I am a very normal person. Okay. An inner product. So when you take the inner product, you take the inner product of x and phi 0. And this is essentially x transpose phi 0 conjugate. This is what we discussed last time. So in general, the definition that we actually, let me put the definition first before we go to the f g vectors. The inner product of f and g is f transpose g complex conjugate. And let's say f has two components in this case, and g has two components. Then fg is the transpose of f. This is f transpose times g complex conjugate. The complex conjugate of a vector is the vector of its complex conjugate. So every entry gets complex conjugated. And so what you have here is f1 g1 star plus f2 g2 star. The reason we have the complex conjugate, you may remember from last time, is that we need to have a situation where, well, inner products must satisfy certain axioms. They must have certain properties. We don't get into those in this class. You get into those in Math 54. In order for the inner product, when you have potentially complex valued vectors, to be satisfied, you need a complex conjugation. Because then, if you don't, you'd have nonsensical things like, if we don't have complex conjugation, if you don't have it, what is that kind of inner product? If you didn't have this complex conjugation, what would this be? I haven't put anything for f yet. This would simply be your dot product. The dot product that you learned in high school was exactly this kind of an operation without the complex conjugation. That's because in high school you only dealt with real valued vectors. And without the complex conjugation, it works perfectly well. But now we're moving into a context where we have not only signals x that can be complex valued, but our ck's are complex valued. They're complex exponentials. So if you don't have complex conjugation, and let's say your f is 1i, then f inner product with itself, which would be the magnitude squared of f, would be 1 times 1 plus I times I, which makes no sense. Because any vector that's non-zero, this is non-zero, should not have a zero magnitude. So that's why you have the complex conjugation. With conjugation, you get something that is sensible. Let's change this to f transpose f, which is f dot product f. What you knew as a dot product would be this. But with the definition of inner product, you have 1i times 1, what? Negative I. And what does that give you? 2, which makes sense. Because you can draw this complex number on the complex plane, and you see that the magnitude squared is 2. Now, back to our expansion. I want to project x onto phi 0. So I take the inner product to find, so project x onto phi 0. Onto C0, sorry. Which means I have to do this. Which means I'm looking at x0, x1, that's my vector, x transpose, into C0, 0 complex conjugate, C0, 1 complex conjugate. So you have the summation over some L from 0 to what? 1, which is, well, okay, we'll put 1. This is P minus 1, because you start with 0 and you go up to P minus 1. X of L, C 0 of L complex conjugate. That's what we've done. In general, to find the second coefficient, I project x onto C1. And I get the sum over all L from 0 to 1, XL, C1 complex conjugate L. So to find the kth coefficient in general, more generally, to find the kth coefficient, I project x onto ck, and on this side I have L equals 0 to P minus 1 XL ck complex conjugate L. I'm not done yet, because all I've done is project the left side of that equation. Remember, we have this equation. X is a linear combination a linear combination of a bunch of these c's, and I'm trying to find the kth coefficient. So here we have summation k from 0 to p minus 1, xk, ck. That's what x is. And I'm taking the projection of the left side onto ck, onto, wait. Now we're going to run into a bit of a problem. Let's make this m. To find the mth coefficient, I project onto the cm. So now I've got to do the same thing on the right-hand side. Wait, let me just make sure we get the notation straight so we don't get confused. I want the mth one. So if I use k as a variable here, I need to have a different variable here. Now, what happens when I take the projection of the right-hand side with cm? Yeah. Mm-hmm. And then, this is the definition of the inner product. To implement that inner product, I have to apply the definition. What is the definition? F transpose G star. Remember, I'm living in the universe of just one period. I'm not looking outside one period. All the actions taking place within one period. And the period I've picked for this case is 0 to p minus 1, or 0 and 1. Okay? So I have a two-dimensional vector. All these are two-dimensional, the ck's. And I'm taking the inner product of my signal x, and the two-dimensional vector is simply the values of the signal x in that period, 0 to 2 minus 1. And I'm taking that inner product with the vector c0. What's the vector c0? Here. Here. It happens to be real in this case, but if p turns into 3, where is it? If p is 3, you won't get 0. You won't get all real values for ck's. But we're living in the two-dimensional case. So I'm taking the inner product of x with c0, and then I have to do the same thing with c1. What is the definition of inner product? Well, you know the signal values. I have to give you those, otherwise you can't do the decomposition. You know the values of the signal. It was 1, 2, 1, 2, 1, 2, right? So it'll be 1, 2 times, what are these values? 1, 1. But this is all only on the left-hand side. On the left-hand side of this equation, I've taken x and I've projected it onto cm. Now, what happens when I project the right-hand side? What about the right-hand side? I have to do the same thing there. I have x0, c0, plus x1, c1. And I've got to take this whole thing viewed as a vector and project it onto c0. What do I get? These two are numbers. So well, let's take it step by step. I have a summation. So I have x0, c0, comma, c0, plus x1, c1, comma, c0. Okay? And now I can take the constants out. x0, c0, c0, plus x1, c1, c0. And what can you tell me about this expression? How can I simplify it further? The second term is 0. Because these two are orthogonal. Because it's 0 because C1 is orthogonal to C0. So on the right hand side you're left with this. So on the left hand side you have x C0, and on the right hand side you have x0 C0 C0. And this is essentially the equation we arrived at last time as well. I told you I'll repeat this as many times as necessary until it finally clicks. So we have the 0th coefficient equal x C0 over C0 C0. What's the first coefficient? You're not going to do this all over again, are you? No! Oh, that was a tortured soul. The same argument holds for finding the next coefficient. In general, the kth coefficient is obtained by projecting x onto the ck and dividing by ck. So let's not forget what our two main equations are. You have k from 0 to p minus 1, xk, ck. This is the signal x, or the vector x, expressed as a linear combination of these orthogonal vectors. And this equation tells you what those coefficients are in that linear combination. In terms of complex exponentials, what does this mean? Well, first of all, in terms of signals, you just put the n dependence. xk, ck, n. And what were our ck's? E to the I, k, omega naught, n. So this is the complex exponential Fourier series expansion of a periodic signal with period p. And this equation is, in some textbooks, called the synthesis equation. It tells you how to synthesize the signal x in terms of a bunch of complex exponentials. These complex exponentials are harmonically related to each other. The only frequencies that can be present in this signal are 0, omega naught, 2 omega naught, 3 omega naught, all the way up to p minus 1 omega naught. You can't have any other frequency aside from these. This equation now, let's see what this says. xk is ck. Actually, we worked this out. What did this work out to be last time? Denominator. P. 1 over P. P. I'll do it again. Don't worry. If you weren't here last time, you missed how we got this to be P. We'll do it again. So it's 1 over P. What is the what is the inner product of x with ck? I'm looking at an interval from 0 to p minus 1. So let's go to this board. Can I finish this equation and then do it? Okay, that's fine. Take your break. Let's get back to work. So in the last lecture, we developed that the inner product of the kth complex exponential sequence with itself is p. I'll do that again today, just to make sure we all understand it fully. But assuming that that's p, you have a p in the denominator, and in the numerator, you have x inner product with ck. And what was that? It's just that sum. L equals 0 to p minus 1 x L C K star L. Okay? Actually, because we have these in terms of n, we may as well just keep this as n. The inner product of x with ck, sorry, is you look at one interval, one period, and multiply the samples of the signal x, the first function, with the complex conjugate of the second function. That's what it is. And what does that translate to? xk is 1 over p summation n equals 0 to p minus 1 xn. What is the complex conjugate of the kth function? E to the negative I k omega naught n. This is called the analysis equation. So we've actually got our two equations. X of n equals a linear combination, where that linear combination goes from 0 to p minus 1, of these complex exponentials, synthesis equation. And the top equation is the analysis equation. That's all there is to the discrete Fourier series story. You say x expanded in terms of complex exponentials. If you can, and to do that, you need to find the coefficients. Can you find the coefficients? Yes, with this equation. In general, whenever you have to expand the signal, more generally, whenever you have to expand a signal or a vector in terms of a linear combination of a bunch of other vectors that are orthogonal, mutually orthogonal, to find the kth coefficient, you simply take the inner product of both sides with the kth signal or kth vector, and on the right-hand side, you only have one term that's non-zero, the one where you actually take the projection of ck onto ck. Everything else is going to be 0. So in the denominator, you're left with ck. What changes from context to context is simply the definition of the inner product. Aside from this, these two equations will be the two main equations. In fact, when I move on to the continuous time story, it's exactly the same equations, except this sum will be infinite, not finite, and the inner product will be defined differently. Let me also just put the last nail in the coffin. When you have two signals, f and g, let's say f and g are signals periodic with period 2. I'm sorry, periodic with period p. the inner product of those two signals will always be n from 0 to p minus 1 f of n g star of n. That's the definition of an inner product of two signals that are periodic. One thing I should mention, though, is that there's nothing sacred about this particular choice of interval. I've picked the interval 0 to p minus 1. It doesn't have to be that way. I can pick my period to be anywhere, as long as I pick p contiguous samples of the signal. So instead of 0 to p minus 1, I could have picked minus 1 to p minus 2, minus 2 to p minus 3. So in general, we use this notation to denote the inner product of two periodic signals of period p. And this means, actually I should say this whole thing means, a contiguous interval of length p. So it could be 0, 1, p minus 1. It could be 1 to p. It could be minus 1, 0 to p minus 2. Whatever is more convenient. If the signal happens to be symmetric, then what kind of interval would you pick? From some negative value to some positive value. Right? If the signal is symmetric, you probably want to go from some negative number to as close to it in the equal on the positive side as you can. All right. So this should be your sacred set of equations. The only thing that changes from context to context is what is the definition of the inner product. And also, at some point, this summation is going to change into an integral. But the fact that x is a linear combination of a bunch of orthogonal functions doesn't change. And that equation doesn't change. Let's do an example. Zero, let's say p, 2p, minus p. This is my signal x. It's 0 all between. An infinite impulse train. Is this a periodic signal? So what I want you to do is find its Fourier series coefficients. Find the xk's. And let's give it a number. Let's use p equals 3. So how many coefficients do you need to find? 3. And it's probably a good idea for you to chat with each other as you do this. In general, when you try to compute the xk's, the coefficients in the Fourier series expansion, whatever answer or expression you get typically has a dependence on k. In this signal, you actually won't get a dependence on k. All the coefficients will be the same. So if you don't get a k floating around in your equations, don't be surprised. This is a very special periodic signal. Okay, Meatball, get us started. The analysis equation. So you've got 1 over p. 1/3. Okay. Zero to 2. So the interval that Meatball is picking is 0 to 2. P equals 3. So what's the 0th term? Times e to the I 0. So plus x sub 1 e to the I k, well, yeah, k omega naught. Negative, yeah. x2 I k 2 omega naught. Okay? Now, what did you say about these two terms? x1 and x2 are 0, so they go away. 0, 0. And you're left with only x0, which is 1, and the denominator is 3. So this is true for k equals 0, 1, 2. And there you have it. This signal can be represented as 1/3 of what? What's C0? 1. C1. Two pi over 3 n, and C2 e to the I 4 pi over 3n. Now, it seems very bizarre that such a simple-looking signal can actually be written as a linear combination of 1 plus e to the I 2 pi over 3 n plus e to the I 4 pi over 3 n. But it can, and it is expandable. Why in the world would we want to do this? Why would we want to decompose a signal into complex exponentials? Well, let me give you a partial answer. xk tells you how much of frequency, what frequency? Fill in the blank, is present in the signal x. What frequency? K omega naught. So the coefficients, the larger the magnitude of the coefficient, the more of frequency k omega naught is present in the signal. If a particular coefficient xk is 0, that means that particular multiple of omega naught, that particular harmonic, is absent from the signal. So essentially the xk's and the k omega naughts go hand in hand. This guy tells you how much of this frequency is present in the signal by telling you what the presence of this complex exponential is in the expansion of x. Another reason why we study this is that we know what LTI systems do to complex exponentials. What do? They scale them. So, you know from before, so we talked about LTI systems and complex exponentials. You know from before that if you send e to the I omega naught n into an LTI system whose frequency response is h, what do you get out? H omega naught n. Okay? What if I send an e to the I k omega naught n? What do I get out? H k omega naught e to the I k omega naught n. And what if I send xk e to the I k omega naught n? I scale that complex exponential by a number. What do I get out? xk h k omega naught e to the I k omega naught n. And hey, what if I now mix and match a whole bunch of these complex exponentials? I take a whole bunch of these complex exponentials and send the package through the system. What do I get out? Huh? Why the pause? It's a linear system. That is a totally unintelligible sound. Summation. That's good. Summation xk. H of k omega naught e to the I k omega naught n. Well, this is your x of n. Periodic with period p. This is your y of n. What can you tell me about y of n? Periodic with p. And if it's periodic with period p, it's got to have Fourier series expansion. Can you tell me what the coefficients are in the Fourier series expansion of y? It's right there staring at you. So your audio equalizer essentially is this hk omega naught. It picks a particular set of frequencies. Now, of course, it's not exactly one frequency. It's usually a set of frequencies around this, because that's dealing with analog signals. But essentially, it takes, when you turn up and down the knob for each frequency band, or each particular frequency, it's this hk omega naught that's going up and down in magnitude. And that's how you get rid of certain frequencies and how you amplify certain frequencies. So decomposing the signal in terms of complex exponentials is useful in our understanding of what LTI systems do. And LTI systems form a very large class of systems that are used in practice. This is not unlike what you knew from before. What happened to my chalk? Where you decomposed an arbitrary but not necessarily periodic signal in terms of impulses, and you sent them through the LTI system, and you got out Y was the same linear combination. So this is a linear combination of these shifted impulses, and at the output you got the same linear combination of the response of the system to each of these impulses, h of n minus m. So this was one way that we looked at LTI systems. The impulses were very special for LTI systems, but so are complex exponentials. So what you see here as the response to the shifted impulse, here you see the response to the complex exponential, the kth complex exponential. So there's an analogy between these two, and that's the connection between the time domain and the frequency domain. So here we've decomposed the signal in terms of a bunch of complex exponentials. At the output of the LTI system, each complex exponential gets scaled by the frequency response value at the frequency of that complex exponential. If the filter happens to kill the kth harmonic, well, then that harmonic is not going to show up in the output. If that harmonic didn't exist in the input, the corresponding xk would have been 0, so it wouldn't have popped up suddenly at the output anyway. So either of these two can ruin the party for this exponential. If xk happens to be 0, it means it just doesn't exist in your input signal. So no matter what the filter does, it's not going to suddenly pop up in the output. And if this particular frequency happened to exist in the input signal and had a contribution to the signal according to the magnitude of this xk, then the filter may amplify it further or attenuate it, just like an audio equalizer would. So these are partial reasons why we decompose signals into harmonics, or in terms of, more generally, in terms of complex exponentials. The story, the way the story is going to evolve is that when we go to continuous time periodic signals, this summation for the synthesis equation, will no longer be finite. Because when you look at one period of a continuous time signal, there's an infinity of points. So something has to give, and what gives is that the summation in the synthesis equation is going to become an infinite sum. Anytime you go into an infinite sum, you have potential issues with convergence. We won't really bog ourselves down with convergence issues. So this summation will go from minus infinity to infinity for the continuous time story. What do you think is going to happen to the analysis equation when we move into continuous time? Here I have a summation over one period. What is that going to change to? An integral over one period, because x is no longer a function of n, x is a function of t, which is a continuous variable. So this summation will turn into an integral, but a finite integral. It's over one period. So that's basically the main thing that changes when we move into continuous time. So I promised I'd develop a couple of equations. I'll do that at the beginning of the next lecture.